Welcome to the lecture on analysis of fluid flow and mixing in Tundish. So, we have anyway talked about the fluid flow analysis and how these fluid flow parameters using that fluid flow we calculate the mixing parameters or the different Tundish volumes which is indicative of the mixing capability of Tundish, how much there will be thorough mixing inside, and what are the dead regions, how the dead volume zone is calculated, all that is we will be discussing in this lecture. So, as we discussed that we will be talking about a particular geometry. So, this is the geometry of a 6 strand billet caster Tundish. This is the work which was done earlier by me. So, even it is reported So, what I wish to show that how the how with the help of a particular problem you can solve you can show that how the analysis is to be carried out and how you understand these the computation of different parameters inside the Tundish. So, this is a typical geometry, again it is a 6 strand billet caster Tundish, and as you see that you will have the 3 outlets 3 to 1. So, you will have in this case we are taking outlet 1 as the remotest one and 2 and 3, and this is your symmetry plane. It means there will be a plane which is going further in this direction, and this is the impact this is the region through which the outlet is thoroughly through that whole zone. So, anyway this is a zone only for that consideration that it is showing the outlet. Then its dimension of the Tundish is also shown. As you see, the height is given and the other dimensions are 2.95 meter of length or so. So, then as usual we again define the grids in the different zones, and you can have the gridded structure, and further you can also use the flow modifiers. So, we have used the flow modifier as the advanced pouring box in this case. We also used the shroud which is there, so that can be used or that cannot be. So, many a times we use this shroud to indicate that the metal will be not exposed to atmosphere and the oxidation kind of problem will not be there inside. Now, as you see this, so once you do the gridding, then you can see that how the gridded structure looks like. Then after that, as you see that you have to solve these equations. In this case we are not solving the temperature, we are solving only the continuity, momentum, turbulent kinetic energy and rate of dissipation. Apart from that we are also solving the concentration equation. So, this is the equation for that concentration, it is concentration of the tracer. So, what we do when we do the these analysis, there are two types of analysis which is being carried out, and that is one is pulse input and another is step input. That is what I think we have talked about it earlier in that stimulus response technique. So, in this case again we are going to have the discussion on that. So, basically what we do that when we have a steady state velocity field set, as we have seen in our previous lecture, that you are going to solve, you have the geometry defined, you are going to define the material properties, you are going to define the boundary conditions at the inlet, at the outlets, at the walls and all that. Then after that you are going to solve the equation and for that you will have these four categories will be there first. So, first you have to solve it, and you will be getting a velocity field. Now, after that you are going to have the tracer concentration solution for the concentration of the tracer. Now, what we do in this case is to know that which of the Tundish is how much good for the mixing, and how the flow behavior is there, how the concentration is changing at the outlets when the something which is coming through the inlet. So, at what time it is going to start from the outlet. So, that also shows, earlier we have seen that it comes through the inlet outlet which is closer to the inlet at a lesser time. So, so that is certainly that does not indicate a very good mixing capability, because it must go into the whole Tundish domain, and then it should come ideally. It should take the ideal theoretical residence time. So, residence time is nothing but volume upon the volumetric flow rate. So, once you know the volume of the Tundish, and if you know the volumetric flow rate, so in that case the ideal volumetric mean residence time is that time which is should be spent by the fluid particle, which will indicate ideal mixing, will be ratio of volume to volumetric flow rate, and that has to be computed. Now, in this case so you are first solving that, and once you solve that, and after that you are again solving for in the unsteady manner. So, in the case of unsteady analysis, what we do is that we have to put the tracer which will be a something like a die. So, that is normally we do the experimental analysis also in this case. So, what we do, we have a colored dye which is injected at the Tundish. So, if suppose you have the inlet here, so you give this colored dye, we are putting it for say 10 seconds and then or even for or less, and then so because it should not alter the flow field inside the Tundish also. So, we are putting also it in the same velocity. So, it will go through that, and then it is stopped, and otherwise the flow continue. After that the flow continues. So, the dye will come and then it will go inside and it will coming out. Now, we have to monitor this concentration of the dye, because whatever quantity has come inside the Tundish, it has to go out, and when its first appearance is there at which outlet. So, that is indicative of the plug component. Similarly, if something is taking more time, more than 2 or 3 or 4 times the mean theoretical mean residence time, then we call it as the dead component. So, if it goes into certain zone, it gets trapped and it takes large amount of time to come out, then it is a dead component. So, that we will discuss, we will see. So, so what is shown is that we get the theoretical mean residence time calculation by volume of Tundish to volumetric flow rate. Now, we have to calculate the actual mean residence time, and normally when you have only one outlet. So, it will be summation of Ci and Ti divided by summation of Ci, that Ci is the concentration which is monitored at the outlet. Normally, it is a dimensionless concentration, concentration divided by what concentration you have put in. So, that way amount of tracer which you have put in. So, basically accordingly you get the dimensionless concentration, that is there, and so we plot a graph between the dimensionless concentration and time, and or if we plot the graph between the concentration and time. So, from that graph basically you can also have the calculation of the actual mean residence time. So, you get a file, normally you have to get a file which will talk about the these concentrations which are coming out through the particular outlet with respect to time. So, you will have with respect to time you will have the concentration. So, you have time 1 second, 2 second, 3 second or so, and you will have the concentration values which will be coming here, and that will be normally initially increasing and then it will be decreasing. Now, because when it has come and it will start entering, that time it will be decreasing, but then slowly once it goes inside the whole domain, then slowly it has to decrease, because you have only injected only a very fixed amount of tracer inside the inside the Tundish. So, so accordingly you see that you get the actual mean residence time, that will be C average IT. C average is taken because if you have in the outlet you have more number of cells are there. So, it will be averaging those concentration values in the all the elements in the outlet domain. Then we calculate these different parameters, like now from these concentration and time graph, a typical concentration curve will look like this. So, it will go like that. So, you will have concentration and time, this is dimensionless concentration, and this delay basically initially, because there will be when you this is at t equal to 0. So, at t equal to 0 when the tracer has entered, it will say take some time to appear through the outlet. So, that time that is known as the the time that from that is indicative of the plug volume. So, that is your breakthrough time, and that is Tp. So, that is first appearance of tracer at the exits. So, and you can get these different fractions. So, once you get the Tp where the first appearance of tracer is recorded, from there you can get the plug volume. So, that is this is Vp, not Vd. So, basically this will be Vp. So, Vp by V will be Tp by tau. Now, tau that this is theoretical mean residence time. Now, what we do is that once you have the theoretical mean residence time defined, and once you calculate the actual mean residence time, so the dead volume will be computed as 1 minus Tr by tau. So, basically we calculate that as the dead regions, because any fluid particle which is taking more time than the mean residence time, they are said to be the dead regions, and that is indicative of those zones which are not effectively being they are not indicating the effective utilization of the whole volume of the Tundish. So, once you get these dead volume and the plug volume, then the difference sum of these values, and then you take 1 minus that value, that will be talking about the fraction of the mixed volume. So, you have three kind of generally volume component inside the Tundish. You have plug volume, dead volume, and mixed volume. So, plug volume will be that volume, as we have already discussed, that it will go without interfering with other things. So, it will be go quietly, and quiescent flow, there will be quiet flow, and then you have the dead volume. So, dead volume, as you see that in the case of dead volume, you have that indicates that this is actually it should be minimum. So, if it is minimum, in that case your mixed volume will be higher. So, that indicates the mixing capability of the Tundish inside. So, because that is required to have a homogeneous temperature inside the Tundish, and also the proper if something is coming suppose through the Tundish, if there will be no mixing or tendency, what happens that if some inclusion comes inside, and if they directly go by short circuiting process towards the outlet, so it will go to the mold. Now, in this case, if you are trying to have a loop inside the Tundish, there will be a chance that this inclusion will be having the tendency to float up. So, that is also another way of which we can see that how you can increase the productivity of the Tundish. So, coming to the results. So, if you first see the velocity vectors as we had seen earlier. So, you have a the outlet plane, and on this if you see the velocity vectors. So, what you see that on this outlet which is near to the inlet, your velocity is quite high, it will come, and then it has also the tendency to go up, and then it is moving like this. So, this is through all the outlets at now in this case we have also changed the position. So, that is why we have 2 and 3. So, position will be 1 as we had seen earlier, that position 1, 2 and 3 can be seen earlier if you see the results. So, in that case it will be shown here. This is position 1 is close to the wall, 2 is away from the wall, and 3 is near the inlet plane itself. So, that way you have these 3 positions just to show you. Now, what you see that in position 1 this switch is close to the wall, what you see is going towards the wall in the top, and then it is moving from there. As we move away from the wall little bit to position 2, then what you see that you see a type of loops also is shown, and it is very evident that you have larger velocities in this zone which is closer to the inlet, and this is near the inlet plane. So, as you see further, the velocity near the inlet is quite high, it is becoming closer to the inlet plane along the length direction. So, you see that there will be changes in these velocity vectors. This you can draw. Now, once you draw, you do the transient analysis. You are having the tracer concentration for some time going through the inlet, and then you stop it after after some time. In that case, you are getting the concentration of concentration variation with time at position 1. Now, position 1 is as you see this is near to the inlet. So, near to the this wall, this side. So, what you see that now you can see this is also called a C curve. So, this is concentration with time. So, as it is known as a C curve. Now, what you see that this is out 1 is away from the inlet, and out 3 is close to the inlet. So, out 3 close to the inlet, what you see, there is a large increase in the dimensionless concentration peak, and then immediately. So, it is at no time you see these values, and then it has a sharp decrease, and then it is slowly decreasing and moving towards these as we move towards the time. Now, the thing is that we take up to 2 times of dimensionless time, and we do the analysis. So, what we see that this larger peak means that there is a short circuiting being taken place. The whatever is coming through the inlet, it is in no time it is just reaching most of the part, most of it's just going through the outlet. So, that is shown by a very large peak in that concentration value. Similarly, as we see for the second outlet, so what happens that the fluid will be entering, striking at the wall bottom, and then it will move. So, it will be some passing will be through the near outlet, and then some will move. So, so from here you can see some lag is there. From here it is at 0 time it is increasing, and here it is maximum. Now, here it is delayed because it is farther somewhat farther from the outlet which is closer to near. Now, in this case it starts little late, and you see that your peak also is somewhat considerably at a very smaller value. This is indicative of the some amount of the plug volume, and in this case, as you see, you might recall that if you will talk about a pure mixed flow, the pure mixed flow will be like this, and the plug will be like this. So, as you see here, you see in this case like this. So, basically you have this is the plug component, and from here you go for the mixed components is this. So, as the peak will be increasing, as there will be higher and higher peak values, it is indicative of the poor mixing capability of the Tundish, and large short circuiting is being taken place, and your dead volumes in that case will be likely to be higher, because the active metal which is coming from the Tundish is not able to move with higher velocity towards the remote places inside the Tundish. So, you can see that you will have a large peak here, and for outlet 2 it is smaller, and outlet 3 it has taken a large delay. So, and then what you see is that is quite a good mixing characteristic is being shown, slowly it is coming down. So, so that is indicative of now, because of this you will have the different value of the mean residence time for the 3 outlets, but we take the average of them. So, if you change the outlet position somewhat away from the wall, in that case that is how you see that this the earlier peak which was 8, because it was close to the wall, once you have taken away from the wall it has come down to close to 6. So, and then this is your 6 C curve for the other 2 outlets, which looks like this. So, if you are further changing towards the inlet plane, you see that it is even smaller, and then that is how. So, you find the value of the mean residence time in these cases, and you just see that how much, because 1 minus mean residence time actual divided by mean residence time theoretical will give you the dead volume region, which should be minimum. So, if you go to find the variation of the ratio of mixed to dead volume, now after this what we do is that we calculate the mixed dead volume. So, that will be 1 minus actual mean residence time divided by theoretical mean residence time. Then you also calculate the plug volume. So, that will be indicative of the breakthrough time. So, when you have the first appearance of tracer which is being appearing, and then accordingly you will have the calculation of the mixed volume also. So, once you know the Vm and Vp, you get the mixed volume, and for representing in terms of fraction, we can have Vm by Vd, you can have Vp by Vd, I mean Vm by V. In fact, we calculate as Vm by Vd is one of the parameter which tells that we try to increase Vm and we try to reduce Vd. So, that will be representing a larger amount of mixing inside the Tundish. It is more desirable feature in that case. So, you will have Vm upon Vd and Vp upon Vd also we can plot, and we try to increase this value of Vm by Vt, and in this case we have tried to show that how there will be variation in the case of Vm and Vd and how their ratio is going to change. So, larger value of Vm to Vd is largely desirable for a Tundish, because it will be indicative of the larger mixed zone and the smaller dead zone inside the Tundish. So, you have variation of risk. So, as you see that once you change the first outlet position is at 150, second is at about 200, and third is about 350 or so, 300. So, in that case what you see is that intermediate position you get this value as the maximum. Similarly, you have mean residence time also, what you see that is the maximum. So, that is so what we saw that at position 2 you can have the maximum value of the mixing parameter calculation. So, to have better characteristics in terms of mixed to dead volume, by altering the flow behavior, as we had discussed in our last lecture, that we use certain type of flow modifiers, and in this case we have used the advanced pouring box as we had shown. And what is shown is that if you use a advanced pouring box of a height of 90 mm, in that case it was reported that you see now when you use the advanced pouring box and you see out 3 is the one which is close to the inlet. Now, in that earlier case it had gone close to 6, but it has now come down to close to 3 or so, not even less than 3. It indicates that when you you put a barrier before the near outlet, before the out 3 in this case, then the fluid goes and it will go into the other part of the Tundish fast. And what you see that you also see a breakthrough time increased. In the earlier case it has started from here, but in this case you start from here, and there is also delay on this and as well as on this. So, it means the first appearance of the tracer is delayed. So, that tells you the plug volume also, and the lower peak will be indicative of the larger smaller dead volume, and ultimately you get larger mixing parameters, mixed to dead volume and mean residence time. So, then even you can change the height of the APB. So, that was also changed, and as you see that once you change the height it was for somewhat increased again this value, and further increased it will give you larger value. But then the value of the mean residence time and mixed to dead volume will be more indicative of what is the mixing parameter. So, that can be computed, and you can also see the change in the velocity field. So, when you use the advanced pouring box, so you can see that you will have the more velocity moving towards the upper side, and then it is moving. You will have some recirculation also. It tells that there will be homogenization and mixing also of the fluids. So, that is a good indication, and it shows that your mixing is improved in this case. So, that is shown with these three types of the heights, and if you look at the variation of the ratio of mix to dead volume, what is shown is that at the middle height, your mix to dead volume ratio is said to be better, although that was having the the peak was somewhat higher for one of the outlet, but otherwise if you look at the overall calculation of the mean residence time, it was larger in that case, and the dead volume was smaller. So, that is why in this case you get a better variation of the the mean residence time. So, you see that for the smaller and for the larger height, it was small mean residence time, whereas it was more for the medium height. Then there can be a study on the shroud immersion, as we discussed. If you do the shroud immersion from the inlet, so accordingly you will have to do the analysis every time. You have to find the concentration and time, and from there you have to calculate these mixed to dead volume function of the shroud immersion depth, and that is for the different positions you can have these volumes. So, that what we see that what this should be the optimum shroud immersion, that also can be computed. With shroud immersion, how the velocity fields are changing, so that can also be seen, that immersion depth of with no immersion, this is how the flow with a height of 210, but if you do the immersion, then how the velocity field is changing. So, there are different velocity field which will be seen with these different immersion depths, and once you have immersion, so it shows that how the velocity field is changing with the box. So, that can be seen. So, what we see ultimately, that when you do the analysis of fluid flow, then and you do the tracer dispersion analysis, by that you can have the calculation of these mixing parameters, different volume components inside the Tundish, like plug, mixed and dead zones inside the Tundish, which is showing the effectiveness of the Tundish. Thank you very much.